Hello, my name is Daniel Joseph. I'm the CEO and President of DR Joseph Incorporated, and I'll be presenting today on the topic of reducing runaway resin for blown film extrusion. This presentation was originally given on Tuesday, June 22nd at Antech 2009 in conjunction with NPE 2009. The paper that goes with this presentation can be viewed by using the Antech search engine at www.forplasticsresearch.org. So let's start with an overview, and what I'm going to do is I'll define for you what runaway resin is, which is a problem that everyone has to some extent. I won't be covering pellet loss in this presentation, but I am going to discuss how chronic thickness variations and oversizing film width contribute to this issue. And then I'll be finishing up with a case study that demonstrates several benefits of automating width control, including one significant benefit we did not anticipate. Just like the hidden leak in this glass of water, there's resin escaping from blown film manufacturing processes. Managers optimistically think that any resin that doesn't become saleable product is simply reprocessed. But as several managers have told me, a fair amount of resin just flat out disappears. One manager told me that the monthly amount lost by their facility was nearly half a rail car. After they made sure they just weren't making accounting mistakes, they concluded that the resin was simply leaving in the products they sold. In other words, they were giving it away by either making the film too thick or too wide. So, for our discussions here, we'll say that the runaway resin is resin that leaves your facility without generating a single penny of revenue. And what makes matters worse is that you are paying for it to leave through your overhead costs. I'm not going to tell you that your goal should be zero runaway resin. And that's simply because there's not a blown film machine on the planet that produces perfect film. But you do need some safety margin to account for even the best machine's process variability. Of course, the tough part is establishing and maintaining the correct safety margin that properly accounts for the machine's true capability. Unfortunately, if your machine's capability produces too much variation, the extra safety margin required to ensure products are within specifications can put you at a competitive disadvantage. Obviously, this is a serious problem, and this can require expensive changes, upgrades, or even the replacement of the machine. Now that I've framed runaway resin for you, let's take a look at two main sources: chronic film thickness and oversizing web width. Chronic thin spots happen more often than you might realize. And older lines without auto gauge control can be finicky every startup with thin spots in the gauge profiles we show here. We all know that regardless of what is causing the thin spots, your operators have to do something to fix it. And depending on the severity, their choices, assuming you have no automated gauge control, include manually adjusting the die gap, which is based on readings from an offline or online thickness measurement device, or simply based on the ability of some operators who can read the bubble shape to tell which die bolts to adjust. For operators who can't adjust a die, why couldn't they just increase the extruder speed? That would add more material to bring the thin spot within specifications, right? Well, maybe not. Here's what's really happening when your operators bump up the extruder speed to correct a thin spot. You can see the entire profile increases proportionally in thickness, resulting in runaway resin, which of course is a problem we're better off avoiding. The final solution is to stop and fix the problem, but unless the problem is quite severe, taking a line out of service for die cleaning or replating simply takes too long. As a result, people procrastinate. And as a result of that, they end up giving away more money in runaway resin than they would if they just stopped and fixed the machine. Next, let's look at oversizing web width. This problem is more prevalent on lines without internal bubble cooling, and this is because an IBC system has a built-in width control mechanism, while lines without IBC have to be sized manually. On the non-IBC line, the operator has to periodically check the size and either add more compressed air or cut holes in the film to release air from the bubble. And the result is a width profile shown here, which you may notice is also showing our chronic thin spot. And over a 12-hour period of time, the repeated cycle of deflation and inflation is clearly evident. The runaway resin occurs because even at the minimum width, the film width is still wider than it needs to be to meet production requirements. Often I have customers who tell me, oh, we sell by weight, so it doesn't really matter. So if they're adding material to cover thin spots and width variation problems, what are they doing to get the weight correct? One customer told me that they take it upon themselves to shorten the bags slightly to get the weight correct, and this is done completely off the record. So regardless of how you cut it, either the film producer is giving away resin or the customer is getting shortchanged. And neither situation is desirable from a business standpoint, and most certainly is not sustainable over the long haul. Can runaway resin be calculated? Well, the answer is yes, with one important assumption, which is that the time to reinflate the bubble is insignificant relative to the time required for the bubble to deflate. If that assumption is allowed, and almost in every case on a blown film line that's true, then the equation for calculating runaway resin is shown here. Note that N is the minimum lay flat during production, SP is the target lay flat specified by the customer, M is the maximum lay flat experienced during production, L is the line speed, and G is the thickness or gauge of the material, and rho is the bulk density in grams per cubic centimeter. And our conversion factor here produces a result in kilograms per hour. So if we were to apply this formula to a theoretical blown film line producing various thicknesses of a 1525 millimeter lay flat with 13 millimeters of total width variation over a 12-hour shift, we would see something like this. Notice that even at 150 microns, the actual material that you were giving away doesn't seem to be a big deal. So if we were to extrapolate that previous result over the course of the day, you could see that there's still not a big deal going on. And once we get out to the monthly accumulation, it starts to make some headway. But when it gets to the annual review, and you see that one small line is giving over nearly 6,000 kilograms of material away, and then you think about how much this would be if you had 8 or 10 of these lines doing this, it starts to add up to a significant amount of resin. Let's take a look at some of the reasons for the small losses that add up to large amounts of runaway resin. The problems begin at startup. The cold inflation air begins expanding almost immediately from the radiation heat coming from the top of the die. This effect continues 30 to 40 minutes or until the internal air temperature of the bubble has stabilized. This effect causes the bubble to swell beyond the desired size unless the operator has anticipated the swell amount, which is something most operators find difficult to master. After the internal air temperature is stabilized, there are small amounts of air that escape from the nip rollers. Of course, when nip rollers are new, this is not a big issue, but over time the crown on the roll wears down and more air escapes, causing the bubble to slowly lose size. Remember my previous point that there are no perfect blown film machines? Well, some of those imperfections can result in small pinholes in the bubble, which allow air to slowly escape, causing the bubble to lose size over time. So taken together, these issues require the operator to pay close attention to the size and make manual adjustments to the air trapped inside the bubble, which of course is proportional to the width of the final product. So as you can see, the dominant effect is for the bubble to lose size over time. So this is the reason the operators will slightly overinflate the bubble and then attempt to later reinflate it before the width falls below target. When they don't make it back in time, however, the product becomes undersized, just waiting to be discovered by the customer. So if externally cooled extrusion dies, we'll call them non-IBC dies, which means they don't have internal bubble cooling. If these dies have runaway resin problems, why is this configuration still so popular? It would seem reasonable that a switch to extrusion dies with both external and internal cooling would be the best way to go, particularly since internal bubble cooling dies also come with a width control system. Well, it's not that clear of a decision for someone who is successful in producing high-value products with non-IBC dies. Why should they worry about improving when they're doing quite well? The unfortunate part about not improving until the need is clear is that it is often too late. It is important to keep your eye on making incremental improvements in your process. Or said another way, a pride of Lions is looking for only one weak performer. For those making medium value films, upgrading to IBC also increases production rate, which may require significant investments in downstream equipment to keep up. With the middle of the road margins, it may be impossible to financially make the jump to IBC control. Another reason non-IBC dies may be preferred is that those dies are very good at producing low volume, narrow width products that are just too small for an IBC die to produce. The smallest practical IBC die is about 160 millimeters or 6 inches in diameter. Finally, one can't overlook that a non-IBC die does provide a low-cost entry point for those wanting to get started in the film manufacturing business. So the bottom line is that non-IBC dies are here to stay. Let's talk a minute about the poor soul who has no college education and maybe didn't even finish high school, and now they have to wrestle with the laws of physics while operating a blown film line. Certainly not something they signed up for. So, as I mentioned earlier, the first problem they have to deal with is that the air inside the bubble begins to heat and expand. So, meaning the operator either has to anticipate this effect, or he simply waits until the bubble stops growing. Once oversized, there's really no choice but to cut holes in the film, creating more scrap. And if they release too much air, they often do, and sometimes lose bubble stability as well, they have to repeat the inflation process. Remember, it's with cold air, which means they have to wait again for the size to stabilize, measuring and starting the process all over. And if they're lucky, if they're very lucky, the total time to production could be around 30 minutes. Let's review why we are bothering with automated width control when the paybacks on automated thickness control are so much better. So, we know blown film in blown film resin is the #1 variable cost. And with energy cost components rising, the reality of reprocessing more material than is absolutely necessary is having an effect on our overhead. It's also having an effect on our carbon footprint. And another way of thinking about this is thinking about if your overhead is going up, which that means that you're having to increase your sales to keep up with the overhead. A good resin supplier friend told me that blown film managers are overly optimistic about the gauge and width variation capability in their factory. In other words, they're blind to runaway resin leaving their factory, just like a glass of water with a hidden leak I showed you earlier. Which means there's definitely some validity to automating the control of film width in blown film extrusion. Finally, the difficulty factor of going with width control is significantly lower than thickness control. So it's better for companies who have little or no experience with automation to take this step instead of starting with thickness control. Here was a plan for our case study. We installed a before the nip width control system using 4 ultrasonic sensors mounted equidistant around the bubble at a height of about 1 meter above the frost line. This setup gave us the ability to calculate and control flat width of the film without waiting for the film to actually become flat. Overall, this type of system gives a much faster startup, size change, and recovery functions over systems that use a flat width bar to measure the width after the film passes through the nip. Our goals? Well, 1, we wanted to improve quality and reduce runaway resin. And 2, we had a goal we wanted to generate a payback of 1 year or less. Not really a goal, but a constraint. We wanted to compare the results with an equivalent 30-day period without control to quantify the benefits. So here's a basic functional diagram of the control system we used for the test. We had a controller that accepts the target value from the operator. We have our width sensing sensors. Again, they're about 1 meter above the frost line. We have our inflation deflation device, which, depending upon what we get back from the width sensing device, controls the size of the bubble. Here are the production parameters for this case study. The die diameter was about 405 millimeters. Average width was about 1220 millimeters. And the average thickness was about 18.75 microns. And you can see the material costs for the LLDPE product they were running. They have a resin to scrap value there of 44 cents per kilogram and a gross margin of 34.6 cents per kilogram. So, the width variation results after the 30-day study showed that we reduced width variation 53%. So, instead of 12 millimeters total variation, we ended up with about 5 millimeters total variation. Our scrap results, they reduced 3.8%. Our runaway resin results reduced about 50%. When we moved into looking at our gross production results, we found that it increased about 7.5%. And what we found was the machine just simply spent more time in production than it did before. And this is because of the faster startups and the recoveries of the small pinholes and things like this. So the line went down less often, and they ended up with 7.5% improvement in net production went up about 7.97%, and it's a little bit higher because we also reduced scrap. So our annualized net saleable was up almost 8%. If we looked at the benefit contributions, you can see that the net saleable is nearly 3/4 of the benefit contribution, where runaway resin makes up 23.8% and scrap reduction is about 2%. If we looked at our investment payback, we found that we were paying back at a rate of 9, that got us a payback in 9.09 months. And this chart here shows basically the initial investment in the light purple color, and then the contributions each month to reducing that initial investment. So by month 10, just into month 10, the entire investment was paid off. So conclusions, well, the biggest savings obviously comes from spending more time in production and less time making scrap. Runaway resins costs are reduced significantly by reduced lay flat variation, but didn't make up as much of the pie as we expected. So the bottom line is that the automated width control did have a significant benefit from improving the net saleable. Scrap reduction was not significant in this instance, though depending upon the operators you have, you might find that there's more benefit on the scrap reduction side than we found. Film quality was improved, and the financial performance definitely justifies installing control systems plant-wide. And in fact, that's what this customer did. They put in 8 units after the results of this study were made known. The other thing is that people tend to swing for the fences and choose grand payback projects over small ones like this one. The difficulty is that the grand projects are significantly more risky, particularly for companies with no experience in automation. So this success with automation has now given this particular facility the confidence that they can move on to something more difficult. And gauge variation control is the next thing on the list of things to do for this company. So if you have any questions about this presentation, I'd be happy to take them by email through my email address here, which is danielj@drjosephinc.com. I appreciate your time in listening to this presentation. Thank you very much, and I hope you have a great day.